Welcome back. In the previous session, we have learned about three very important terms regarding the heat transfer by radiation. They are the absorptivity, transmittivity, and the reflectivity. And then we also have learned about what are the laws that governs the three phenomena, and we have found out that Kirchhoff's law or the Kirchhoff's law is the one which describes the three phenomena that we have described. And then Kirchhoff's law says that the absorptivity is equal to the emissivity of the body when the two bodies that are in thermal equilibrium. Therefore, this is very profound finding that we got. In this session, we are going to study the new concept regarding thermal radiation, that is the intensity. So it is denoted by small letter I. So intensity actually in the Lambert term is how bright the things are. Since we know that heat transfer by radiation is concerned with the heat transferred by electromagnetic waves, we can see that this can be also associated with the property that is intensity. So in order to understand the fundamental definition of intensity, it's very important for us to understand what is the solid angle. Now in the 2D, we define the angle in radians. Then in the 2D, we have solid angle, where we denote as omega. So in 2D what we have is how we define angle in 2D. We have a circle which has a center of C. Then we draw a line, which this is the radius of the circle. Then from this point A, and then we go and travel by the arc of S, right? And then if you join this, okay, so this line is also the angle theta. This line is also the radius. Therefore, when I traveled the arc S along the circumference of the circle, the angle traversed that I get is the theta. Therefore, we get that our S, the length of the arc that we get, is the product of the radius times the angle in radians. For the full circle, we know that the arc that we travel is equal to the circumference of the circle. Therefore, we have circumference of the circle is 2 pi r with the radius of r. Then we get that the full circle, the angle in radian that we get is 2 pi r by r is 2 pi radius. Now this is the way that we define angle in 2D. So what about the solid angle now? This solid angle is the 3D projection of the angle that we define. For example, you are standing here and then you're looking at the far away door. Okay, we have a door like this, and then the door has the width of this 30. So you're looking with your eyes from here, and then you're looking at the extreme side, this side of point A, and then you're looking at this side of point B. So what is the angle traversed? This theta, this is 2D angle projection that is same as the angle that is measured in radians. But now how do you infer in the 3D angle? We get that if you again consider the height of the door. For example, the height of the door is h. Then your eyesight also should look at this, right? Now your angle projection is in 3D, right? So you know that this angle 3D that you obtained is equal to, or is called, the solid angle. In the Lambert term, when you look at the door and just you're concerned of the one dimension only, and then you are trying to figure out what angle of view angle, thus your view is covered by the object that you can see. In one dimension is called the angle that you measure in the one dimension. Whereas, what is the pitch? What is the point of view covered when you look on the all three dimensions is called the solid angle. Therefore, the solid angle is the 3D version of the angle that we see. Okay? To understand more, it's very important for us to recollect the spherical coordinate. So we have done in the previous class during the derivation of the heat transfer in cylindrical coordinate, right? As well as spherical coordinate. Therefore, to remind you, the spherical coordinate looks like this. This is a spherical coordinate where we have three axes, Cartesian axis. Z, Y, equals X and Y. Now you have the point, which this is the 0, 0 point. And then you have some point at this point P. And the distance in 3 dimensions is given by rho. Such that your rho now is x squared plus y squared plus z squared whole root. It's the expression of the rho. Then what you can get is that you project from here, set an angle from here, and you find some points here. So you have the two angles, that is the zenith angle of phi and the azimuth angle of phi and the zenith angle of cosine. Zenith angle of theta. So this zenith angle can move along this in 0 to pi direction, right? Therefore, the freedom of the zenith angle we define is pi and 0. Whereas for the azimuth angle we have phi is has freedom to have the full rotation, which is 0 and 2 pi. So if this is the case, then this will be rho sine of theta, and if this is the case, then this will be also rho sine of theta. Then if you join this, your x equals to what? Is rho sine of theta cosine of phi, y rho sine of theta sine of phi, and z equals to rho times cosine of theta, and then this is the point. So if you square this all, then you will be able to get this as rho. And this is how your spherical coordinate is being defined. Now we are going to get some area in this cylinder. So I know that I'm ejecting some area of like this. I want to find what is the area here within the cylinder, right? So I can see that it can move along this direction. This area, I can move along this direction, as well as I can move along this direction. So this area that I can now say as A, B, C and D. So this area A, B, C and D has the two angles that you have to take care. That is the zenith angle and the azimuth angle. Now we know that this one, in order to find this, we have to find the length of this and the length of this to find the area of this patch, right? Therefore, it's similar to finding a volume, elementary volume for the cylindrical coordinate. Spherical coordinate, what did we get? We got the expression last time as elementary volume equals to rho squared sine theta d phi dr d theta. This was the expression for the elementary volume. So what is the expression for the elementary area that you are trying to find? Now from this, you know this distance that you get is already rho times sine of theta. So this distance now you are trying to find is what? This distance or this arc that you are trying to find is subtending the angle of this angle, the zenith angle of d phi. Therefore, this arc that you are trying to find, which is AB, is equals to what? This AB is equal to rho sine theta times d phi. Now what about this length? You know that this from center is R, right? So what is the angle that is moving up and down? This is actually the zenith angle, right? Therefore, when we take a very small elementary area here, you are traversing the small zenith angle of d theta. Now, the expression for arc that you have is r times d theta. Therefore, our CD equals to r d theta. Therefore, the area now is what? Our area ABCD, which is elementary area, equals to, this is rho, right? Therefore, you can say is rho squared sine theta d phi theta. Now, what is the geometrical interpretation of the definition of the solid angle? The solid angle is the ratio of the elementary area dA, the patch area that you get, divided by the square of the radius of the sphere. So in the 3D, the radius of the sphere is exactly the rho, right? So when you divide this, this actually is this expression for the solid angle. Therefore, the whole hardship that we did is to define what is the solid angle. Now we have the expression of this one as dA. Therefore, we can now define solid angle in the spherical coordinate by using spherical coordinate as rho squared sine theta d theta d phi upon rho squared, which in turn gets sine theta d phi d theta. So this is the expression for the solid angle. Now, as we know the definition of the solid angle as well as the formulation, now we are ready to define what is intensity. Okay? To define this, let me draw this simple diagram here. Consider there is a very small area of the emitter body that you see here, like this. This is a very small emitter body with a differential area of A. And what you're trying to do is, as this is the source of the thermal radiation, you know that it will give the radiation in all the directions. And it will be in the hemisphere that you know and we have discussed in the class. From here, I want to draw a normal to the surface, which this is a normal to the surface. And then I want to take some area here. Okay? Some area of A1 here. And then need to find what is the solid angle subtended here. So if this is in 3D, then this angle is actually my solid angle subtended like that. Right? Therefore, what is the radiant flux? Okay? Which is, we know that the total radiant flux with the hemisphere will be E. But when you count the radiant flux in a very small area of A1, then I'm only counting very small portion of the whole radiant flux. Therefore, only dE amount of radiant flux will pass through the area A1 that I am putting inside. Therefore, my intensity, now radiant defined intensity I equals to the ratio of the small radiant flux that you can see divided by, when you project this area, what is the solid angle subtended? This one. So this is the definition for intensity of the radiation. Okay? And then this is very important. You box it. Now, let us see the Lambert Cosine Law. Suppose you have the radiation here. I will take the same example and draw a very simple diagram now. So this is the surface here, and this is source S. And I have drawn one line here, which I said is a normal. And then I have just measured this angle theta like this in 3D, but in 2D, this I am just doing is, what is this angle here? Just angle has a freedom of moving here to there. So this actually is in 3D, and in 2D is actually my angle of theta, right? In 2D I will get angle of theta, that's a zenith angle. So in the 2D I'm saying is, this is the intensity of radiation that I found in the direction which is theta angle away from the normal. Okay? But the only thing that I get is the value that is incident, which is along the normal, which I get is IN. So this incident ray is the incident ray which is along the normal of the plane that I have written. And this plane is actually the surface area of the emitter plate. So, I want to find this I now. How should I find this? Well, you can just use the trigonometry and say that this I is actually IN cosine theta. Do you see you involve some cosine here? And if this is constant, right, I can say I is proportional to cosine of angle. So this expression is called the Lambert Cosine Law. So Lambert Cosine Law is helpful in order to find the intensity at any direction which has angle in 2D subtended of angle of theta with respect to the normal, provided you know the incident ray which is at the same direction to the normal. Okay? Therefore, this is called the Lambert Cosine Law. Now, we got the things that we need in order to find the intensity and how it is done. Okay? Now, what I will say is, I want to find the intensity here, or I want to find the emission power from this equation by using the intensity. From here, I can replace this by IN cosine theta, right? So by doing that, what now I will get is that by doing this, what I will get is now IN cosine theta equals to dE by d omega, such that if I want to find dE here equals to what is the emission power, total emission power, hemispherical emission power of the radiation by using the intensity here, then I can use IN cosine theta d omega. Right? Now, how can we find this? In order to find this E, just I have to integrate this and I have to integrate this also. From the equation, we know that our d omega is what? Is sine theta, right? D theta and d phi, which is here. So I have to substitute this here, and when the integral is whole over the hemisphere, I will get the emission power, total hemispherical emission power equals to this In is constant, right? So I can take outside. Now I am struck with this 2 integral, which is double integral. Why? Because I have to substitute this first. Cosine theta, sin theta, d theta, d phi. Because this is actually the value of this one. Since we have two angles here, theta and phi, we know that my phi can run around or have complete full circle, right? So it is outside, so I am going to give a bound of 0 to 2 pi. Whereas inside, right, inside theta, I am going to restrict from 0 to pi by 2. Okay, therefore 0 to pi by 2. This is how we have to do the integral. So when you do the integral, what do you get now? When you do this, now I get E equals to In. There's something common here. How can you write this? Cosine theta, sin theta. Oh, we can write this as half of sin 2 theta, right? So I can say half of, I don't want to integrate this phi right now, so I can say here, to isolate the phi, d phi here and 2 pi. Keep this aside, you don't need to worry about. The only thing that you have to worry is now, 2 is already included here, therefore I have only is sin 2 theta, 0 to pi by 2, d theta. So what is the value of integral of sin 2 theta? That you may wonder. It is now that we have In by 2, 0 to 2 pi, right? D theta times. This is actually minus cosine of 2 theta divided by 2 from 0 to 2 pi. So this is reduced to very simple integral. From here we can write In by 2 times 0 to 2 pi, right? No, this is 0 to pi by 2. Sorry, this is pi by 2 d phi. So when I put this one, so I can get this minus of half. It's all minus of a half here. When I put 2 times pi by 2, what am I getting? I am getting this cosine of pi. So cosine of pi is minus 1. Then minus, what if I put cosine theta as 0? Then I will get is cosine 0, which is 1. Then this much. From here, you can see that this is minus 2 and this is minus 2. So it will get cancelled and it will return positive. Therefore, the only thing we are left is by 2, 0 of 2 pi of d phi. Correct? Now to solve this, we are now going to have to integrate this In by 2 times this one, d phi is phi from 2 pi to 0 equals to In by 2 to pi 0 equals to 2 will get cancelled and pi times In. So what did we find? We found out at last that our emission power, total emission power, is related to my In as this one. If you just multiply the In value that you have times pi, you will be able to get the emission power of the whole sphere in this setup, where In is the emission at the normal plane. Now you want to have this inside the equation. What should you do? Just you use this and say, you can say as E raised to E equals to pi times, just you put this In and it will give I times secant theta. So this is very profound law. What does it say? Once again, if you know the incident ray intensity at which is subjected to normal line, okay, this only thing that you have to know. Then if you multiply with the pi, then it will just give the intensity, emissive power of whole sphere, which is the total radiant flux, okay, at all wavelength. So this is very powerful law, and this is the Lambert Cosine Law, and this is the intensity. I hope you would have understood the video, and I'll see you in next video. Thank you.